What I'd like to do now is rather quickly go through the linked list code for an actual implementation of the linked list data structure. Now, this is a somewhat simplistic implementation. It doesn't take into account a lot of the error handling cases that a production class would need, and it only implements a subset of the truly useful behaviors that a linked list offers. But it gives enough insight into how the linked list works that I think it's a good foundation to work from. So we begin with the linked list node. Now this is very similar to the node class that we've already looked at several times in the module so far. Only this time, you can see that the linked list node takes advantage of the C# generic syntax. This allows us to hold not just integers, but any type of object within our linked list. One more deviation from what we've seen is that we've added a constructor. And this constructor allows us to create a node with a pre-specified value. This is just a little bit of syntax sugar to help with creating nodes. Otherwise, the node is nearly identical to what we saw before. It has a value, which is the generic type, and it contains a pointer to the next node in the chain. Very simple. So let's go and take a look at the linked list class. Well, the class is about as simple as it can be. It also is a generic type, meaning that the linked list can contain nodes that hold any type of data. And it implements the iCollectionT generic interface. And this interface provides a certain set of operations that all collections that implement this interface are guaranteed to expose. Implementing this interface helps us conform with some .NET conventions and ensures that we'll be able to drop in where other collection types are used without having to change any existing code. So as you would expect, we have the pointer to the head node and the pointer to the tail node. These are auto-implemented properties, so they default to the value null. They have public getters, but private setters, because the list should be managing these values and nothing else. Now we have add methods and remove methods. These are the methods we saw in the earlier slides, so I won't spend a lot of time going into them. But what you'll see is that we have add first, which allows us to add a value into the list, and we'll create the node for them. Or add first where a node is provided, and we'll just add that node into the list. Additionally, we have add last. And add last also has a direct value and a node with value. Add last also allows adding by value or adding a node directly. Now these are the same implementations we saw in the slides. Likewise, remove first and remove last. And again, these are exactly what we saw in the earlier slides, so I won't spend any more time going through them. And that leaves us with the iCollection interface. There's a few things in here we haven't looked at, so it's worth going through. And we have the count property, another auto-implemented property with a public getter and a private setter. At any moment, the count property will indicate the number of nodes that are currently in the list. The iCollection interface guarantees you have a way to add an item. This implementation simply defers to add first, adding the item to the front of the list. iCollection adds a contains method. The contains method performs a simple enumeration over the list and returns true if a node with the specified value is found. This enumeration pattern matches what the getEnumerator does, only it puts the behavior in line with the enumeration. iCollection requires the copy_to method, which allows us to copy all of the nodes from the linked list into an array. And again, it's the basic enumeration pattern. Only the behavior internally, instead of yielding the result, is performing a copy of the value into the pre-allocated array provided by the caller. The iCollection interface also has isRead-only. Now, this collection is not read-only, and it never will be, so we just return false. And here we get to a method that's a little bit more complex. And this is a version of remove that we haven't looked at yet. And the way this one differs from the removes we've looked at is that it doesn't require that the item be removed from the start or the end of the list. It allows an item by value to be removed anywhere within the list. That's a little more complex. There's 4 cases we need to care about here. We have an empty list where nothing's done. We have a list with a single node where we just want to remove that node if the value matches. And we have a list with many nodes. And within the many nodes, we distinguish between removing the first node in the list and removing any subsequent node in the list. The algorithm is pretty straightforward. While we haven't iterated to the end of the list, it's our basic enumeration pattern, we're going to check if the current value equals the value we're looking for. And if it does, we're going to remove it from the list. If it doesn't, we're going to move on to the next value. Now, one way this enumeration differs is that we're not just storing the current node, we're also storing the previous node. And we're storing the previous node because it's possible that we would remove a node in the middle, and we need to be able to update that pointer without having a helper. Now recall when we removed from the end of the list that the tail pointer allowed us to do that very easily. Well, in this case we don't have a tail pointer, so the previous variable serves as a proxy for that. So let's look at that example. So if we're coming through and we find that we've matched the value, and previous is not null, which means we're not the first node in the list, because previous was null up until one time through this while loop. In that case, we're going to take the previous node we found, which is not the node that matches the remove criteria, and we're going to set its next pointer to be the current node, which we are removing, next pointer. So basically we're skipping over the current node. So let me draw this out real quick. If the before were the nodes 3, 5, and 7, when we're removing node 5, the after would be 3, which would be previous. Its next pointer would now point to 7, which is current's, or 5's, next pointer. So that's what we're doing here. It's just jumping over the node we're removing. Now, if current.next is null, which would be a case where we were removing 5, but there was no 7. So for example, it was 3, 5 null, and now we want it to be 3 null. Well, in this case, we also need to update the tail pointer, because the tail pointer previously would have pointed to 5, the last node in the list, and now needs to point to 3, the last node in the list. And regardless of what position we were at, we decrement the count. Now the other case here is the case where previous equals null. And in that case, we've encountered the node we're looking for by value the very first time through the loop, which means it's the very first node in the list, in which case we can just call remove first. Now if we removed an item, which we did if we're in the equals condition, we return true. Otherwise, we'll eventually have current be null, break out of the enumeration loop, and return false. So that's a little bit more complex of a remove operation. So take some time and look at it and think about how it works, and look at some of the tests. Now the enumerator is what we looked at in the slides. It's unchanged. iCollection also requires another enumerator, which is a non-generic enumerator. So we just defer to the specific enumerator we've written. And finally, iCollection requires clear. Clearing a linked list is very simple in a garbage collected environment. You just set head to null, tail to null, and count to 0. We can do this in C# because what that will do is remove all of our references to every node in the node chain, and there'll be garbage collected. If this were a language like C or C++, where garbage collection is not performed by the system, but a responsibility of the programmer, you would have to, at this point, dynamically delete each node in the list. So that's our linked list class. As you can see, it's pretty straightforward. There's a lot going on, but it's not that complex. I would encourage you to take some time, look at the code, and get a feel for how it works, and then see how you can extend it and how you might make it more robust. A challenge I would throw out is the case of add last that takes a node. What if the node provided was part of a different list already and it wasn't the last node? Well, the node.next wouldn't be null. So we'd come through here and we'd have a bug, because when you enumerate, node.next would still be set to the other list. In fact, we would enumerate from one list and jump all the way into another list. So there's a lot of things to think about that we're not going to go through and add the robustness for, but that I think would be good exercises for you to think about and to try and handle.